Hello everyone, I am Himanshu Mishra, and this week is the continuation of the last week. So last week we actually discussed about the kinematics of a system, but in a rotating frame. So this week also we will solve few problems related to the rotating frame. So we will solve few more problems to find the velocity and acceleration, relative velocity or relative acceleration in a rotating frame of axis. So as usual, um, we will start with very basic concept of fundamental concept and the fundamental expression that we will going to use in all our questions, and that might you have seen in the NPTEL lectures. So why we use the rotating frame of axis and what is the expression of velocity and acceleration? So that we have already discussed, but let's begin with that. So let's say I have a fixed coordinate system which I am representing by capital X and capital Y. Let's say there are 2 points. There is one point A and there is one point B. And let this there is one position vector RA and there is one position vector RB. Then there is one position vector R. Okay, and now in the red color I am actually drawing the rotating coordinate system. So this rotating coordinate system is actually rotating with, let's say, angular velocity omega, which is theta dot, and it's making an angle theta from the fixed axis. Then I can write the position vector RA equals position vector RB plus R, right? Now I need to calculate the velocity, and for that I need to differentiate this expression of position vector R with respect to tan. So it will be R dot A equals R dot B plus d by dt x plus y. So this is my vector R. Now how the coordinate will rotate? How should I connect the rotation of a coordinate with the angular velocity? So for that, let's say we have a coordinate here y and x. This is my rotating coordinate. Right, now this rotated to this new axis. It is rotated by d theta, and here also it is rotated by d theta. So this is small j and this is I. This is my x, right? So you can see both x and y direction rotated by d theta. So this d theta will be dj cap equals minus d theta I. You can see that. So this is my y axis and this is my x axis. Sorry, this is my x axis. This, and both are going to rotate by amount of d theta. So this is my x axis and this is going to rotate in the jth direction. Similarly, this is my y axis and it is going to rotate in the ith direction, negative ith direction, because it's in the left hand side direction. So my rate of change of jth cap will be, this is the amount of rotation d theta and this is the direction, ith direction. This is minus ith cap direction and this is positive j cap direction. So this rotation I can write as d I cap equals d theta j cap, right? So I can write d I cap equals d theta j cap. So if I differentiate this in time, I will get d I cap by dt, d theta by dt, and j cap. So it will be I cap dot equals omega j cap. Similarly, I can write j cap dot equals minus omega I cap from this expression. And if I, so this is the scalar equation, and if I want to write in the vector quantity, it will be I cap dot equals omega cross I. Similarly, j cap dot equals omega cross j. So if I want to differentiate this part, I need to differentiate with respect to x as well as with respect to I cap. So it will be r dot b plus x dot I plus y dot j plus x I cap dot plus y j cap dot, right? Now I can substitute the I cap dot and j cap dot expression in this one, in the black color one, and on substitution I can write the expression for velocity. So this will be my expression for velocity. So this is the velocity of point A in capital XY coordinate. This is the velocity of point B at capital XY coordinate. And this is the relative velocity in rotating coordinate XY. And this term is the difference between the relative velocity from rotating and non-rotating coordinate. Right? Now I can actually extend this figure 1, to explain the each term here in this expression. Let's say this is my point B and this is point A, and we have here the rotation coordinate system. So there is a plate which is aligned to the rotating coordinate system xy, small x and y. Now you can see that let me make a bit more bigger diagram. So there is a point here which is A, and this is capital Y, this is small y, and this is small x, this is capital X. Now you can see that this rotating coordinate which is shown by the blue color is actually moving. It is actually rotating with some angular velocity omega, and this point A is also moving, which means the point, there is some velocity of point A with respect to this rotating coordinate which I am marking by P. Then there is a velocity of point A with respect to B. So there is a point which is moving inside this space, right? And the velocity of this point A with respect to B is this. it is actually in the this direction, whereas the velocity with respect to the rotating frame is in the tangential direction, this. And the velocity of point with respect to B. So this is the velocity of rotating frame with respect to B. It is actually normal direction. So I can make the parallelogram here. And this velocity is actually can be given by omega cross r. So this is velocity of rotating frame with respect to B, which is given by omega cross r, and this relative velocity is actually given by this, which is the velocity of point A with respect to the rotating coordinate system, and it is actually in the tangential direction. So if my particle is moving, it is in the tangential direction here, and the normal direction will be omega cross r, which is the velocity of rotating frame with respect to point B. And the absolute velocity will be the velocity of point A, basically velocity of this point with respect to B, right? So this expression can be further written as V equals VB plus V point with respect to B plus V relative velocity, and this is my omega cross r. So this is the expression, this or either this, that we are going to use in our calculation. And similarly, if you differentiate this velocity expression, you will get the acceleration term. So which can be written as velocity of point A, velocity of point B, both are in the capital XY direction. So this is my expression for the acceleration of point A in the fixed frame, and it depends on the acceleration of point B in the fixed frame, and these two are the component of acceleration in the normal and tangential direction. So this is the component of acceleration in the tangential direction, and this is in the normal direction, and this is my Coriolis acceleration, and it depends on the angular velocity of the rotating frame as well as the relative velocity in the rotating frame. So as we discussed in the last class very briefly, that this Coriolis acceleration occur only in the rotation frame of axis. So for example, if you don't consider the rotation frame of axis, then this Coriolis acceleration will be zero. So this occur only when there is a presence of the rotation frame of axis, because it's depend on the velocity which is given in rotation frame of axis. Then this is my relative acceleration in the rotation frame. So except this Coriolis and this relative acceleration in the rotation frame, every other term which I am showing in the blue color actually given in the fixed frame, and this is my unknown acceleration of point A in the fixed frame. So we are going to use these two expression here to find the velocity and acceleration of a given point, or to find the relative velocity and relative acceleration, or it could be also the angular velocity and angular acceleration, and so on. So let's start with solving problem. So here we have given an instant represented a disk with a radial slot is rotating about O with a counterclockwise angular velocity of 4 rad per second, which is decreasing at the rate of 10 rad per second square. The motion of a slider A is separately controlled, and at this instant R is 6 inch, R dot is 5 inch per second, and R double dot is 81 inch per second square. Determine the absolute velocity and acceleration of A for this position. So here we just need to calculate the velocity and acceleration, and we are going to use those expressions. So in the last class, most of the question that we have solved is only the substitution based. So if you remember the formula, if you remember the concept, you know how to find this various component of velocity and acceleration. So for example, to use this expression and all, you need to identify what is the relative velocity, what is the relative acceleration, and what is the Coriolis acceleration. So once you figure out all this component, you can easily use this expression, and you just need to substitute. So in this question, we need to find the velocity and acceleration of point A. So the velocity expression is VA equals omega cross R plus relative velocity, because there is no other point. So in the previous example that we have shown, there are 2 points A and B, and we wrote the expression of velocity and acceleration of point A with respect to point B. So we have given the velocity and acceleration of point B here, and with that respect we actually wrote the relative term relative velocity, and we write down the velocity of point A with respect to velocity of point B, and also we add the contribution of relative velocity. But here there is no B point, so our equation of velocity of point A reduced to omega cross R plus relative velocity, right? And what is the relative velocity? So you can see that this point is actually moving in this direction, which I am showing. Let's say this is my disk, this is O, and this is the block, and let's say this is my small x, and this is my small y, right? And you can see that this block can actually move in only small x direction, and also this disk is rotating, so there will be a relative velocity of this block with respect to this disk, right? So if my block is moving with r dot, which is 5 inch per second, so this velocity is actually the relative velocity, because this block is moving in the rotating disk. So this block is moving in the straight line, and this whole straight line is actually rotating with some angular velocity along with the disk. It is rotating with some angular velocity omega, which is the angular velocity of disk. So this is my this is my relative velocity of the block, and omega we have given, which is 4 rad per second. And now we need to determine the position vector r, and for that we have given r, which is 6 inch, because we have given a instant, at a suitable instant where we need to find the velocity and acceleration, and at that instant my r is 6 inch, right? So you can see this, all these values are given in the magnitude or in the scalar quantities, and this expression you have given in the vector quantity, so you need to convert everything into the vector quantity. So your relative velocity vector is, the magnitude is 5, and you can see this, that this block can only move in the small x direction, right? It can either move here or it can either move here. So basically it can move only in the small x direction or in the I cap direction, and this is a relative velocity because as it is moving in the small x direction, this disk is rotating, right? So there is a translation motion, and disk is also rotating, which means this is a relative velocity because you are there are two kinds of motion, one rotating motion and one is translating motion. So this is my 5i omega, and my omega is, the magnitude is 4 rad per second, and as you can see this, it is actually rotating in the counterclockwise direction, which means the axis of this angular velocity is out of the screen, right? So it is 4 k cap, and my position vector is 6i. So if I substitute in the above expression, I will have VA equals 5i cap, sorry, 4k cross product with 6i plus 5i. And we know that if I do the cross product between k and I will get the resultant value in the j direction. So this will be my resultant direction, and my magnitude will be 24. So I will get 24 in the jth direction plus 5 in the x direction, which I denote by I cap. So this is my velocity vector at point A. And to find the magnitude, I will use this expression 24 square plus 5 square. So my velocity at magnitude of velocity at point A will be 24.5 inch per second. Now we need to find the acceleration. So the expression for acceleration is already given here. So again, there is no contribution from this term because there is no acceleration at this point B. There is no point B at all. So my acceleration expression will be omega cross r plus omega dot plus r cross plus 2 omega cross plus so this was our expression, and as we discussed earlier, this is the relative acceleration in the rotating frame, and this is the relative velocity in the rotating frame. These two terms are the components of acceleration in the inertial frame. This is in the tangential direction, and this term acts in the normal direction, right? So if I have a block here, which is, and this is my coordinate system, small x and small y, which is a rotating coordinate system, then this is the direction of omega dot cross r, and this is the direction of angular acceleration, sorry, acceleration at point A, and this is the direction of omega cross r, right? Similarly, in terms of velocity, this is the direction of relative velocity, and this is the direction of omega cross r. So you can see that if you take the derivative of this, you will it should be this direction, right? So this is the direction for omega cross r here. So we already know omega vector, which is this 4k, and r vector, position vector, which is 6i. We just need to plug in here, and the relative velocity vector, which is 5i, and this is my magnitude of relative acceleration, which is 81i. So I will have so we also given the omega dot, which is 10 rad per second, and you can see it's in opposite direction of omega. So this is omega dot will be minus 10 k cap. So this omega dot will be minus 10 k cap multiplied by 6 I cap, right? And the Coriolis term will be 2 4 k cap cross product with the relative velocity, which is 5i, and the relative acceleration is 81i. So now we can solve term by term. So let me take the first term here. So this is my first term, this is second term, and this is third term, this is fourth term. So if I took the first term, so you can see if you do the cross product between this inside the bracket, it's between k cap cross with I cap. The resulting quantity will be in the j cap, and the magnitude is 24. So it will be 4 k cap cross with 24 j cap. Now you have to do the cross product between k cap with j cap. So the resulting quantity will be in the I cap. And the magnitude will be 96 I cap. Similarly, the second term will be it's a cross product between k cap with I cap, which will give you the result in j direction with the magnitude of minus 60. And the third term it is 8k cross with 5i, So the resulting term in the jth direction, and the magnitude is 40. Right, so we got all our vectors. So on plugin we have, so the first term we have 96i, so this is k and j, right? So it will be minus 96. The second term is minus 60 j. Third term is plus 40 j direction, and the relative velocity is in x direction, so it's 81i. So you just separate out all x and y component. So it will be minus 15i minus 20j. So this is the acceleration vector at point A. And if you want to find the magnitude, you will be using this 15 square plus 20 square. So magnitude will be 25 inch per second square. So just to recap here, we have given a system, a disk which is rotating with some angular velocity and angular acceleration, and there is a one small uh, slider which is translating in the along the x-axis, along the small x-axis here, and we need to find the absolute velocity and acceleration of that uh, slider. So it is a straightforward problem because we use the formula here for the velocity of a slider. And for example, to use the velocity of slider expression, we need to find the relative velocity as well as the angular velocity and position vector. So the relative velocity is basically is directly given in the equation, which is 5 inch per second, because as you can see that the slider is moving in the small x-axis direction with 5 inch per second square, and at the same time this disk is rotating with some angular velocity. So there is a relative uh, motion occurring between the disk and the slider, right? So this uh, velocity of this relative motion is actually 5 inch per second, which is given here. So you need to identify that. For example, let's say there is a slider which is moving, which is translating, and this whole system is rotating. So you can see there is a relative motion between this slider and the whole system. So whole system is rotating and slider is translating. So there is a relative motion occurring between the slider, this, and this whole system. And you need to figure out the velocity of this relative motion. So the velocity of relative motion is basically the velocity of this slider, because as this slider is translating, the whole system is also moving at the same time. It is also in the motion. So the velocity of slider is itself uh, given in the equation is the relative velocity. Now we need to find the absolute velocity of the slider. For example, if let's say absolute velocity means that if this disk stop rotating, then what is the velocity of the slider, right? Because this velocity of slider, which is given by VA, is the velocity of slider in the inertial frame. This is the velocity at inertial frame, right? So what happens if my disc stop moving? Then what is the velocity of a slider? So that we have need to find. So for that we use this expression here. we actually use this expression here, and we figured out the relative velocity expression, and we have already given the omega and the position vector, so it was just a straightforward problem, and we got this vector, which is the velocity of slider in the inertial frame. Now to find the magnitude of this vector, it is a simple procedure. You need to take the square of it, both component, and you actually found 24.5 inch per second. Now again you need to find the acceleration. So for that, this is the expression we use, and it is made up of acceleration in the normal direction, acceleration in the tangential direction, the Coriolis acceleration, which was given in terms of relative velocity. So this relative velocity given in the rotating frame, and the relative acceleration, which is again given in the rotating frame. So out of these four terms, two terms are given in the inertial frame, and the remaining two terms are in the rotating frame. And we need to find the acceleration of a slider in the inertial frame. This is the absolute acceleration, which means if you stop rotating the disk, what is the acceleration of the slider? So in the inertial frame we need to find. So for that, we just substituted all our expression in this equation. We substitute all our quantities like omega dot, position vector, relative velocity, and the relative acceleration in this expression, and it is just a straightforward equation then, and we found the vector, acceleration vector, which is given by this, and we take the square of the component to find the magnitude of the acceleration. So now let's move to the next problem. So here at the instant shown, rod AB has angular velocity 4 rad per second and angular acceleration 2 rad per second square. Determine the angular velocity and angular acceleration of rod CD at this instant. The collar at C is pinned, connected to CD, and slides freely along AB. So first let's make a schematic diagram here. Right, so this is my rod A, B, and this is C, and this is D. Right, now CD is rotating with some angular velocity that we need to find, and it also has some angular acceleration. And my rod AB also rotating with some angular velocity and angular acceleration. So the angular velocity is 4 rad per second and angular acceleration is 2 rad per second square. And let's say my coordinate system is aligned so this is my small x and capital X, and this is my small y and capital Y. So small y and small x, these are my rotating frame, and capital X and capital Y is my inertial frame. And this distance is 0.75 meter, and this distance is 0.5 meter. So we need to figure out the angular velocity and acceleration of rod CD. Right, so in order to find the angular velocity of rod CD, let's find what is the velocity of this point C. And in order to find the velocity of point C, we have already given the point A, so we can use the relative velocity expression in the rotating frame. So let's say this is my velocity c, which is equal to velocity a plus omega cross rc. Okay, so this expression we already discussed in the beginning of class and also in the previous lecture, right? So this is the velocity of point c in the inertial frame, that is in the capital xy coordinate, and this is my velocity of a in the inertial frame, right? And this is the relative velocity in the rotating frame, the small x y axis. And this is also in the inertial frame, right? So you can see that from the figure, this at point A this bar is hinged and there is no translating motion of this bar at point A, which means that my VA equals to 0 and my acceleration at point A is also 0. My omega is 4k, so this is rotating in the counterclockwise direction, and the axis of this rotation should be out of your screen. It should be perpendicular to the screen or perpendicular to the paper, which means this omega is 4k rad per second, and my omega dot, which is acceleration, angular acceleration, is 2 rad per second, and this is 2 k cap rad per second. Right, so if I substitute in the velocity expression here, I will have Vc equals Va, which is 0, plus omega cross Rc. So first we need to figure out the position vector as well. Which is 0.75 in the x-axis. So you can see this is 0.75 in the x-axis, so this is in the I cap direction. So now when we use this expression, we have Vc equals omega, which is 4k cross with 0.75 I. Plus VCA, and we don't know about this, the rotating frame. Right, so this is my equation 1. And in the previous lecture we also used a simple expression to find the velocity, which is omega r. So this is my scalar notation. So for example, if my rod is moving with some angular velocity omega here, then at the end its translating velocity can be given by omega r in the scalar form. In the vector form, it will be omega cross r, right? So the velocity of point C, this can be given by omega of this CD. So this is omega CD cross RCD. So this is my vector position notation. So I can use this expression also, because as you can see, this expression contains two unknown. This relative velocity is also unknown quantity, so I cannot use this expression alone. So what I can do is I can use this expression. I can write Vc in terms of omega CD and RCD and then equate here. So at the left hand side I will have this expression, and at the right hand side I will have this expression. So my omega c will be, so this is unknown. Omega cd is the quantity we need to find. It's in the kth direction and we need to find the rcd, the position vector for this, right? And it is given 0.5 meter. And since it's a position vector, we can actually calculate the component of 0.5 meter in the small x and small y direction. So basically in this direction as well as in this direction, right? So my RCD is 0.5 cos 30, because this is my 30 degree, this is the 30 degree in the ith direction, minus 0.5 sine 30 in the jth direction. So this will come out to be right. So this is my position vector. So now I can use this expression. So my velocity vector at point C is omega cd in the kth direction, cross product with 0.433 I minus 0.25 J. I am considering I here because I am assuming this is in the clockwise rotation. So now I can take the cross product. So if I take the cross product between k cap and this term I cap, I will get the resulting quantity in the j cap. So it will be 0.433 omega cd j cap. Similarly, if I do the cross product between k and j, I will get the resulting quantity in the I cap, and the magnitude is omega cd multiplied by 0.25. So this is my magnitude and my direction is this I. Right. So this is the velocity vector for point C, and this is equation 2. So now I can equate equation 1 here with equation 2, because both are the expression for velocity at point C. Right. So this term we can calculate. So it's a cross product between k and I. So the resulting quantity in the will be in the j the direction, and the magnitude is 4 multiplied by 0.75, which is 3. So this quantity will be 3j. So 0.433 omega CD J plus 0.25 omega CD I equals 3J plus VCA I. So you can see that now you have one equation and you have two unknowns. So these are the unknowns, omega CD and VC with respect to A. And you can actually separate out the X and Y component. So this is your Y component, this is your Y component. Similarly, this is your X component and this is your X component. So you will get two equation. In X component, it will be 0.25 omega CD equals VCA, and in the Y component, it will be 0.33 omega CD equals 3. So here you will get omega CD as 3 by 0.433. So this will give you 0.692 rad per second. So this is our angular velocity of our CD, which is 0.692. And then from the first expression here, 0.25 omega CD is 0.692 equals velocity of point C with respect to A, which is 0.173 meter per second. So this is the relative velocity of point C with respect to A, and this is the angular velocity CD. And in order to calculate the acceleration, we will use the similar expression that we have used for the velocity here. So this is a velocity of a translating velocity of an end point, which is C, which is given in terms of angular velocity and position vector. Similarly, I can write the expression for acceleration of point C, which is angular acceleration cross product with the position vector minus omega square CD right, because the acceleration will have two components, one in the tangential and one in the normal direction. So this will be my expression for the acceleration vector at point C. So using this, you actually get the vector of acceleration. So we have already given the angular acceleration, and we have also given the angular velocity. So for that, you can use here to find the acceleration.
Sir, can you zoom out your screen a little bit? I'm not able to see full. Yeah, thanks.
Yeah. So just to recap here, we have given a rotating bar here, and we have been asked to find the velocity and acceleration of rod CD here. So for that, what we use, we actually try to calculate the translating velocity at point C first, and assuming that there is a point A, so we use the expression for the relative velocity of point to find the translating velocity at point C, and it is given in terms of the translating velocity of point A and the relative velocity between A and C, plus there is some angular component as well. Now accept this relative velocity which is given in the rotating frame, all other velocity given in the inertial frame. So basically what does Vc means, what is the velocity of point C given that if you stop the angular velocity and angular acceleration. So in case this rod is not rotating, the angular velocity and angular acceleration is zero, then what is the velocity at point C? So this is what velocity of point C in the inertial frame means. Inertial frame means the frame is not rotating, and if it is not rotating, then what is the velocity of point C? So for that we have used this equation. Now if the frame is rotating, then you need to find the relative velocity component, which is given by this thing. So this is unknown. So we use two expression here. First we use this expression and we got the vector equation in terms of relative velocity and the unknown velocity of point C in the inertial frame. So remember, this is in the inertial frame, whereas this velocity in the rotating frame. Relative velocity will always be in the rotating frame and this Vc in the inertial frame. Then since there are two unknowns, we use this expression. So in the last few classes we have been using this expression to find the translating velocity. So in the instantaneous center tutorial we use this expression a lot to find the translating velocity. So we use the same expression and we write down the another equation for translating velocity of point C. So we equate both equation 1 and 2 to find the unknown angular velocity of bar CD as well as the relative velocity of point C with respect to A, right? Because when we talk about the relative velocity, we are actually considering both motion. We are considering the most angular motion of this rod as well as the translating motion of this point C. But when we are actually finding these things Vc and this Va, we are assuming that these are the motion, these are the velocity of a point when there is no rotating frame. So these are the velocity of point in the inertial frame, which means these are the translating velocity of point C when there is no rotation. So these are the absolute velocity of C. Whereas this term will give you the velocity of point C with respect to A when there is a rotation as well as the translation of point C. So there is a translation of point C and the rotation of a whole system, whole coordinate system. So there is a relative motion occurring, and to quantify those relative motion, to find the velocity of that relative motion, it can be given by relative velocity, and its acceleration can be given by relative acceleration.
Sir, can you give us idea about the motion of this uh, free body? I was confused well since it is sticked at sea. How it can rotate?
No, it is not sticked. So it is stick to the one point A. So it's already given in here. So this is stick to point A and it is trying to rotate this whole bar in the counterclockwise direction, and as it is rotating in the counterclockwise direction, this there is a translation motion occurring in this slider. It is either going up or it is either going down, and this bar is
So
also
CD bar also will move.
yeah, so CD bar is also moved. So this is what we found here. So we actually found
Okay,
the
okay.
angular velocity of CD, and we also found the relative velocity of point C with respect to A. So this is why we use this expression, because you can see this slider. See, this is actually this actually having the translation motion, but this whole system is also rotating. So there is a relative motion between this translation motion of slider as well as this motion which is occurred by the system which is rotating. So there is a rotation of system and there is a translation motion of slider, and due to these two different motion, there is a relative motion occurring, and the velocity of this relative motion will be vc with respect to a. This is what we found. And this vc, this vc is actually the velocity of point c. So this is actually the velocity of this slider in the inertial frame, which means if you ignore the rotation of this system, then what is the velocity of slider? So this is that velocity. Similarly, this is the velocity of point a in the inertial frame, which means if you ignore the rotation, then what is the velocity of point a in the inertial frame, which is 0 in this system. So let's move to the next problem. So it's a similar problem here. So here we have given the quick return mechanism consists of a crank AB, slider block B, and slotted link CD. If the crank has the angular motion shown, determine the angular motion of the slotted link at this instant. So we have given the angular motion of crank here. The angular velocity is 3 rad per second and the angular acceleration is 9 rad per second, and we need to find the angular motion of this slotted link.
Sir, where is point A here?
Oh, sorry, point A is this.
Okay, thanks.
So this is my slotted link here. This is my small y and capital Y, and this is my small x and capital X, and I am assuming that at this instant my rotating frame and inertial frame are coinciding with each other. So this is the slider, and this is rotating with omega and alpha.
Okay, that is slider.
Yeah.
Slider exhibiting translatory as well as angular motion.
Yes, so this point B will exhibit the translating motion, and this whole slotted will exhibit the rotatory motion. So there will be a relative motion occurring between them.
Okay, with related to slotted link, it is translatory. With related to crank, it is rotatory. The block.
No, so there is this point B is actually translating, and this whole CD, bar CD will try to rotate. So there will be a rotation of CD, and at the same time, this AB is also rotating, which creating this translating, because you can see this block is actually constant. So it's either move, it can only move in this direction. So this point B will have a translating motion, and at the same time these two rods are rotating as well. AB is rotating, CD is rotating, whereas B has translation in the fixed direction.
Okay, sir. So, but with the block is translatory with respect to CD link, and is it not rotatory with respect to crank? Like with crank, it is also rotating.
Yeah, yeah. It is rotating with crank as well.
Okay. Sir.
So, so if I use the expression between point B and point C, then I will have, so this is the velocity of point B in the inertial frame. This is also in the inertial frame, and this is a relative velocity in the rotatory frame. And we have given omega here. So here the velocity, translating velocity at point C will be 0 because this is fixed. So my VB will be, and I don't have this relative velocity of D with respect to C. So I need to find this velocity in the inertial frame. So basically velocity of this point, and there I can use omega AB cross RAB. So we know omega AB and we know RAB as well. So with respect to this y and x, which is this, so I have here, so this is my R. So let me a bit think about this position vector RAB. So I want to write this position vector RAB in the xy coordinate. So this is 60 and this is 30. So if I write in terms of, so if I write this RAB as point, so the length is 0.1 cos 60 I cap plus zero point 0.1 sin 60 j cap, and my omega AB is 3 k cap. So VB equals 3k cross product with zero point 0.1 cos 60 I cap plus zero point 0.1 sin 60 j cap. So VB vector will be if I do should be J, should be I. So 0.3 cos 60 I, zero point 0.3 sin 60 J. So this is my VB vector. Now I can use this expression here. So my VB vector is this. So VB is 0.3 cos 60I plus 0.3 sin 60J equals omega cross RBC. And we don't know this omega because this is, so this expression is between velocity of point B and velocity at point C. So basically this part. So this should be the angular velocity of slotted link, which is this part, which is unknown, which we need to find. So omega CD in the kth direction cross product with RBC. And RBC is this. So this distance. And it is actually given 300 meter. Plus relative velocity, which we don't know. So this is our expression here, and again like previous question we have two unknown, omega CD and V velocity of point B with respect to C. So in the x component I will have this part. So this is k cross I. It will give the resulting quantity in the j cap, and this is the I cap. So these two are the x component. So zero point 0.3 cos 60 equals v point b with respect to c, and 0.3 sine 60 equals 0.3 omega cd. So these are in the jth direction and these are in the ith direction. So velocity of point B with respect to c will be 0.15 meter per second, and omega cd is sine 60, which is 0.866 rad per second. So this is my omega cd. Now in order to calculate the acceleration, I can use the same expression. So it will be AB equal to AC plus omega dot RV with respect to C, then omega cross RV with respect to C, plus Coriolis acceleration cross with relative velocity plus relative acceleration. So this is the acceleration of point C in the inertial frame when it is 0, and this is the tangential part of the acceleration in the xy frame. This is the normal part of the acceleration in the capital XY frame. This is the Coriolis acceleration, and it is actually the cross product of angular velocity with velocity within the rotating frame. So if you ignore the rotating frame, then the Coriolis acceleration will be 0, and this is the acceleration in the rotating frame. So this acceleration you will get when you differentiate this velocity expression in time. So you will get this part. Now you need to figure out AB. So in the previous question we actually figured out velocity VB by using this expression. Similarly, for the acceleration we can use AB equals angular acceleration cross with RAB minus omega square RAB. So from this we actually can figure out the acceleration at point B. And then we will substitute all the equation here. So omega dot is, this is actually alpha CD. So omega dot is alpha CD. So alpha CD cross product with 0.3 I plus omega is 0.86 that we found actually in the kth direction. And this omega is 0.866 in the kth direction. 0.3 I plus 2 0.866 the kth direction multiplied by 0.15. This is the relative velocity we found in the ith direction, plus the relative acceleration we don't know, right? So now you can figure out the terms here. So this is k cross I, which is, so the this can be given as 0.866 multiplied by 0.3, which is the magnitude, and k cross I, and the resulting quantity will be in the jth direction. The magnitude is 0.259. So this is, when you multiplying this number, it will come out to be 0.259 in the jth direction. Then you will have this term, the whole term. So this is 0.866 k multiplied by this 0.259 in the jth direction. So when you have k cross j, the quantity you will get in the minus I direction. And the magnitude is just a multiplication of this term, 0.866 multiplied by 0.259. So this whole term will be 0.224 I minus, and this alpha CD is in the kth direction, so this whole term will be in the j, because k cross I will be j cap, so this whole term will be in the j direction. And magnitude is 0.3 alpha CD j. So your equation will be here, AB 0.3 alpha CD j minus 2.4 2.22 I, and then we need to find the Coriolis term. It is the cross product between k and I, so the resulting quantity will be j, and the magnitude is multiplication of 2 into 0.866 multiplied by 0.15, which is 2.598. So this is my Coriolis term, and this is my relative acceleration in the ith direction. So this will be my equation. So for AB, I will use this alpha AB cross R AB minus omega square R AB equals this RHS term. So when you solve this, again you will get the equation in terms of alpha CD and ABC, and you can actually split the component like we have done for the velocity case, split the x component and y component case. So the one component will give you the relative acceleration and one component will give you the angular acceleration. So this relative acceleration will be 0.104 meter per second square, and the angular acceleration will be, so this is between C and D, right? Yeah. And the angular acceleration will be 3.23 rad per second square. So it will be the similar problem. So we just use this expression for the velocity case. We figure out the relative velocity between point B and C and the velocity of point C to use this expression, but the velocity of point B was unknown as well. So for that we use this omega cross R for the velocity B and put back in this equation. And the same thing we have done for the acceleration. So this is the expression for the acceleration, and since this is 0 and we don't know about this acceleration at point B, so we use this expression at point B, substitute back here and find the unknown quantities. So you can see in the both ways you just need to figure out few quantities like relative velocity or relative acceleration, position vectors, and the angular component of velocity and acceleration, and then it is just the substitution based problem. You just substitute all the quantities in the big governing equation, like this is for VB and this is what acceleration, to find the quantities. So even in the previous question we did the same, but we actually found only the velocity part. So we used the same velocity expression, and then we use omega cross R to find the unknown velocity of point C, and then by splitting the component in x and y direction here, we found the angular velocity and the translating velocity, and the same thing we have done here as well. The only difference is here we also use the expression for the acceleration as well. So this is the general expression for the acceleration, and this is the general expression for the velocity that you need to use. So let's move to the next problem. So it's a similar one, and we have given a slotted arm AB, and which is pinned at point A, and it is rotating at angular velocity AB. We need to find the angular velocity of link CD. So we have given the angular velocity of one arm, and we need to find the angular velocity of another arm CD. So this is AD, and this is CD. This is my x-axis, and this is my y-axis. This is 30, and this is 45, and this is 15. So this AD has the angular velocity, sorry, AB, which is 10 rad per second. And we need to find the angular velocity of CD. So if I use the velocity expression between point D and point A, then I can write as VD equals VA omega cross RAD plus the relative velocity of point D with respect to A, the rotating frame. So again the same velocity expression here. Right? And we don't know about VD, and VA is of course 0 because it is pinned. So this is 0, and we don't know VD. So VD we don't know, but we can actually get from this bar, because this bar is rotating with omega CD. So VD will be omega CD cross product with RCD. Right? And omega CD is unknown, and it is in the kth direction, whereas RCD with respect to x and y axis is given by 450 millimeter, and with respect to x and y axis it is 0.05 meter cos 15 in the ith direction in the x axis plus 0.45 sine 15 in the y direction. So my VD will be omega CD k cross product with 0.45 cos 15 in the ith direction and 0.45 in the in the y direction. So if I do the cross product here, I will get positive j. It's 0.45 cos 15, so this is 0.434 omega CD in the jth direction, and k cross j will give negative I. So the direction is negative I, and the magnitude is 0.45 sine 15 multiplied by omega CD. Which is 0.116 omega CD. So this is the velocity vector of point D. So I can substitute this here in this general expression here. So it is 0, and first we need to figure out other terms in the general expression. So omega we already know here. Omega, this is omega AB or AD, and RAD is zero point 0.6 meter in the x direction. You can see here, which is RAD is just a 0.6 in the ith direction, and we don't know about the relative velocity of point D with respect to A. So it will be, so we have VD equals omega cross RAD. So omega is 10k and RAD is this 0.6 in the x direction, plus relative velocity in the ith direction, and this VD is given by this expression. So it's a similar exercise. So the magnitude here is 6 and the direction is j because it's a cross product between k and I. So this will be 6j plus relative velocity in the ith direction. So just split into x and y direction. So this is my x direction and this are my y direction. So in y I have 0.434 omega CD equals 6. So omega CD is 6 divided by 0.434, which will give you 13.8 rad per second. And in the x direction you will have 0.116 omega CD equals v relative velocity. Omega CD is 13.8, so which will give you the relative velocity 1.6 minus meter per second. Right, so it was again the straightforward problem. So in all of this problem you can see that we need to find, we have already given the angular velocity of one bar and we need to find the angular velocity of another bar. So what we are doing when we are writing this velocity expression, we are choosing 2 points. In this question we choose point D and point A, right? And we wrote down the velocity expression between these 2 points. So this velocity of point D can be given in terms of velocity of point A and some relative velocity between these 2 points, right? So you need to choose any two fixed point. Now once you choose a fixed point, what happens that you need to figure out this velocity at point D because it is unknown, because if it is rotating, there is some translation at velocity at point D, there will be some non-zero VD and you need to figure out. So for this we actually use the simple formula omega cross R to find the velocity at point D. Now when you use this omega cross R, you need to consider this omega, this angular velocity, because you are considering now this length. So basically if this length is rotating, then what is the translation velocity at point D? So here you need to consider the position vector of this bar and the rotating angular velocity of this bar. But when you use the general formula between 2 points, then you need to consider the angular velocity and position vector of between these 2 points, which is point A and D. So we use this equation omega cross R, where omega and R is actually belong to this rod. But when we use the general formula between point D and A, then we use omega and R between point D and A, which is shown by this blue color. So we equate these two equations together to find the omega CD and the relative velocity. So it's a similar problem. If you have any doubt, you can ask. So any doubt until now? So let's move to the next problem. So here we have given at the instant shown boat A travels with the speed of 15 meter per second, which is decreasing at 3 meter per second, while boat B travels with a speed of 10 meter per second and increasing at 2 meter per second. Determine the velocity and acceleration of point A, boat A with respect to boat B. So basically we have given the velocity and acceleration of both boats here. So this is my boat A. It is actually moving.
Yeah, again zoom out properly. Yeah, thanks.
Anyway, I will upload this PDF after this lecture. So you see that.
Okay.
So this is boat A going with a 15 meter per second, and there is an acceleration in the negative direction, which means it's a retardation. And this is my boat B, which is moving in 10 meter per second, and it has the acceleration in the same direction, which means it is increasing the speed, right? And both these are actually moving in an arc which have the radius of curvature. So this is 50 meter and this is 50 meter, and this is my y and small y axis, and this is capital X and small x. So it's basically it's given in the directly in the question that we need to figure out the velocity of boat A with respect to velocity with respect to boat B. So if I write the velocity expression of VA between these 2 points VA and VB, then it will be omega VB plus omega cross R plus relative velocity in the rotating frame. So here what we need to find. So in the question we have been asked to find the velocity of boat A, velocity of boat A with respect to B, which means we need to find this relative velocity, right? Because this is the velocity of boat A with respect to B, whereas this is the velocity of boat A in the inertial frame, and this is the velocity of boat B in the inertial frame. And you can see that this velocity of boat A is given 15 meter per second in the y-th direction. So it is 15 j meter per second, and velocity of boat B is minus 10 j because it is moving in the opposite direction. It is moving in the minus y direction, meter per second. Acceleration of boat A is negative. So so you can easily estimate the velocity of the boat based on the diagram that it is moving north or in the south direction, and in the same manner you actually write the vector quantity. Since it is moving in the north direction, the velocity of boat A is positive. If it is moving in the south direction, like boat B, it is in the negative j direction. But for the acceleration, you need to find the tangential and normal component. So in the question, it is given that there is an acceleration of boat B here, which is in the south direction, negative y direction. So this is a tangential acceleration, because in the previous lectures we saw that if there is a point A here, then there will be a two component of acceleration. This is the tangential acceleration and this will be your normal acceleration. So unlike velocity, where you simply write the velocity vector based on the diagram, like 15I for VA and minus 10, sorry, it's a J, minus 10J for VB, you cannot do the same with the acceleration, because this acceleration is actually the tangential component of acceleration and you need to find the normal component of acceleration. So the tangential component of acceleration of boat A is minus 3J, because it's in the negative y direction, and the tangential component of boat B is minus 2J, right? But the acceleration vector can be written as a tangential component plus the normal component. So you need to find now what is the normal component of acceleration. So my acceleration of boat A will be the tangential component plus the normal component, and the normal component is given by VA square by radius of curvature. VA is 15 square by radius of curvature, which is 50 meter. So which is 4.5, right? And the normal component will be towards this point, right? Because it is rotating along this curve. It is right. It's rotating along this curve like this, and therefore the normal component of acceleration is always towards point O, which is in the negative x-axis. So it will be, then the acceleration of point A will be minus 3J, which is my tangential component, and then minus 4.5 I, which is my normal component of acceleration. Similarly for point B, my normal component of acceleration is VB square by rho, and my VB is 10 square by 50, which is 100 by 50, which is 2, right? So my acceleration of point B is, my tangential acceleration is minus 2I, which is this, minus 2J, which we have already written, minus 2J minus 2I. No, sorry, this will be positive 2I, because this boat is moving like this, right? It is moving like this. So it will be toward this point, the normal acceleration toward this point O, which is the positive x direction. So this will be plus 2y. So this is the normal component and this is the tangential component, right? So whenever you need to write the acceleration vector, so the bottom point is, don't just see the figure and write down the acceleration vector. You can do the same thing with the velocity. Just see the figure, see the magnitude given, and see the direction of the velocity, and based on that you can actually write down the velocity vector. But you cannot do the same thing with the acceleration, because for the acceleration there are two components, normal and tangential. So from the figure you can actually write down the tangential component of acceleration, but then you need to calculate the normal component. of the acceleration. And to calculate the normal component, you can use this expression, v square by radius of curvature. And then the acceleration vector can be written in terms of tangential and normal component. So this is the acceleration vector of both A and B, and these are my velocity vector of both A and B. So now I can use this velocity expression as well as the acceleration expression. So here I know this VA, I know this VB, I don't know this omega, and R is R is 30 I. It's given here 30 meter. So we have given this, and we need to find this relative velocity. So this is the unknown we need to find. So first let's figure out what is the omega here. So we have used the expression. So in the previous question we actually use omega cross r to find the velocity at point D, as well as even in the previous question we use the same expression. So from past 2 or 3 question we have been using the formula v equals omega cross r. So in the magnitude manner, so this is a vector notation. In the scalar form I can write v equals omega r. So my omega will be v by r. So I can use this. So my r is the radius of curvature, and v is already we know what is v. So omega for velocity, this will be, say, Vb by rho. So this is 10 by 50, which is 1 by 5, or 0.2 rad per second. And I can find omega dot as v dot by rho. So v dot is my acceleration, it's a tangential acceleration, abt by rho, and abt is 2 by 50, so it's 1 by 25, 0.04 rad per second square. So we now know omega, we also know omega dot, so this is also known. So now we can easily use this expression to find the relative velocity. So my Vb is minus 10j. Sorry, it's between A and B. So my Va is 15j, Vb is minus 10j, omega is 0.2 in the kth direction. The kth direction is out of the screen. Cross by minus 30i plus v relative in the ith direction. Now it should be the jth direction now, because the boat is moving in the y direction, right? So the relative velocity will be in the jth direction. So this is the cross product between k and I, so it will give me the resulting quantity in the jth direction, and the magnitude is 0.2 multiplied by 30. So this will be 6 minus 6. So it will be 15j equals minus 10j minus 6j plus v relative in the jth direction. So every component in the y direction only. So it will be 15 equal minus 16 plus relative velocity. So my relative velocity will be 15 plus 16. So my relative velocity will be 31 meter per second. So this is my relative velocity, and similarly I can find the relative acceleration. So for that I need to write the expression for acceleration. Just a minute. So acceleration between point A and B will be acceleration of boat A in the inertial frame, acceleration of boat B in inertial frame, omega dot cross R A B. So this is the tangential component plus omega cross R. This is the normal component plus Coriolis acceleration plus the relative acceleration that we need to find. Right? So this is the same formula we have used earlier in the question. Here we have acceleration of point, then we have a normal component, then we have a tangential, then we have a normal, then we have a Coriolis, and then we have a relative. Right? So we already know all this stuff. So we know this, we know this, we know omega dot, we know this. So we know each of this quantity and we need to find this one. So AA is, we just found AA, which was minus 4.5 I minus 3J. Equal to AB, which is 2I minus 2J plus omega dot was 0.04 rad per second plus RAB, which is 20I plus this term, and the omega was 0.2 K cross with 0.2 K cross with R, which is 20I plus Coriolis term, which is 2 multiply 0.2 in K direction cross product with the relative velocity that we found, which is 31 meter per second in the jth direction. 31 in the jth direction plus the relative acceleration in the jth direction. So this is the expression we need to solve. So you can see both I and J component are there in the expression. So let's first simplify this expression. So it's minus 4.5 I minus 3J equals 2I minus 2J, and the cross product between K and I will give quantity in the jth direction. Magnitude is 20 multiplied by 0.04, which is 0.8 in the jth direction. And this quantity K cross J, it's J, it's I. K cross I, it will give me the jth component. So this quantity will give me jth component. The magnitude is 20 multiplied by 0.2, which is 4 minus 4J. Then this is 0.2 K multiply cross product with minus 4J. So the overall quantity will be in the ith direction, right? Because this quantity is 0.2 K cross product with minus 4j. Magnitude is 0.2 multiplied by 4, which is minus 8.8, and the k cross j will give me ith component in x direction, 0.8. So this whole term is minus 0.8 I. Then the Coriolis term is k cross j, and the resulting quantity will give me something in ith direction, and the magnitude is 2 multiply 0.2 multiply 3, so it's 0.4 multiply 3, so it's 1.2 I plus relative acceleration in the jth direction. So we can solve for all I component, and then we have to club all I component and j component together. So when we do this, we will get relative velocity as 4.3 I minus 0.2 j. So this is the vector of relative velocity. So just to recap here, so this was a quite interesting question, because here we have given the velocity and acceleration of both A and B. So from the figure we actually figure out the velocity vector of both A and B, but you cannot do the same with the acceleration. So from figure you actually figure out the tangential acceleration, but then you calculate the normal acceleration by formula v square by radius of curvature. So from the tangential and normal acceleration, you actually write down the acceleration vector, which is the summation of these two components. So then you write down the acceleration for both A and B and velocity of both A and B, and then you use the general formula between point A and B. So by using that, you can able to figure out the relative velocity and the relative acceleration of the boat. So any doubt? So if not, then that's it for today. The remaining few questions we will solve next week. Thank you.